Hi, everybody. Welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. Today, I'd like to continue with the second video on computational physics. And we're going to be doing basically integration, or what used to be called quadrature. And I just want to remind everybody that on my site, I have my I've reorganized it so it's right on the top, but the first thing that I have is the PDF of my chapter 1 for Kunin's book on computational physics. I think it's about 20 pages long right now. It's expanding rapidly. And then I have the notebook here. I need to update this. I will update this as soon as I'm finished with this video, but I update the PDF every time I'm finished with it. So I've made a bunch of changes, and while the PDF, the links aren't active, I added some navigation and everything and some corrections. And, so now it starts with navigation, and if you want to go somewhere, you click on that, it takes you right there. I should have another navigation thing back to the top, but you can just scroll. So today, as I said, I want to do what's called numerical quadrature. And Kunin uses the word quadrature to distinguish it from integrating a differential or partial differential equation. And quadrature is sort of like an old-fashioned term, but there's a lot of things like we'll get to Gaussian integration or Gaussian quadrature in a few weeks. But they used to have to calculate these integrals, and they didn't have computers. And people like Gauss and many other people invented a lot of fancy ways to actually do these things. So I want to go through this notebook. I recommend either having a PDF on the side that you can look at. I realize the print and everything is really small, but there's nothing I can do with that right now. If I try and make it bigger, well, maybe that made it a little bigger. I have to go back there. Yeah, I guess that helped a little bit. Let's see if I can do it again. Okay. I think if I do it again, I'm going to go off the page. Yeah, I don't want to do that. Okay. So, with numerical quadrature, the idea is very simple. We want to calculate a definite integral. And I notice also that for some reason my mouse doesn't show in this window. So there's really nothing I can do about that right now. I have to try and fix that. I had it before where it was showing on some windows, but it's not showing on the windows I'm using right now. So anyway, we need to calculate a definite integral, the integral from a to b of f of x dx. And in calculus, I think almost all calculus courses today, they teach the trapezoidal rule and Simpson's rule, which is given below and I'll get to in a second. And these methods are based on dividing the integration integral into like n equal parts of length h. That's the key thing. They're all the same length. And so you can calculate h by b minus a over n. It's important to realize that n is the number of intervals, not the number of points. The number of points is actually n plus 1. So if you have 2 intervals, you're going to have 3 points. And the trapezoidal approximation is based on a linear approximation. You just draw a straight line after you divide the intervals. In each interval, you draw a straight line from the beginning to the end, and then you integrate that. Very easy to do. The Simpson's rule uses a parabolic approximation, second-order quadratic polynomial, and it uses 3 points, and it uses 2 intervals side by side. And then higher order formulas use higher order polynomials and more points. So I'll just briefly I want to mention this is important, as Kunin mentions. Quadrature is stable, unlike numerical differentiation, where oftentimes you're subtracting two almost equal properties and you have real problems with round off error and everything. With quadrature, at least in the formulas that we're going to use, you're always adding the same positive quantities. Everything is positive, so you're adding positive quantities, so round off error is not as much a factor. You still have the problem that in Python, at least, the precision on your computer is about 16, 17 significant digits. So that's always going to be a problem, a limitation. And we'll see, for instance, like the trapezoidal rule, a quick estimate of the accuracy is of order h squared. So if h is like 10 to the minus 8th, then you're going to be at the 10 to the minus 16th. So you don't want to go smaller than 10 to the minus 8th for h, because at that point in time, it doesn't improve your calculation. We'll see that later. But so 10 to the minus 8th for h corresponds to 10 to the 8th intervals, or 100 million intervals. That's a lot of calculation for doing one integral. But that's with the worst formula we have, the trapezoidal rule. We'll see with the Simpson's rule. It's generally of order h to the 4th. So there we stop with h at about 10 to the minus 4. And the number of intervals is about 10,000. So that's feasible, and we can do even better, as we'll see. I want to point out one thing, that Kunin's treatment here is very terse and very quick. He doesn't prove anything, or even he derives a couple of things, but he doesn't really prove anything. But there's another book, as I mentioned in the references before. Let me scroll up there. This book, Computational Physics, Revised and Expanded by Mark Newman. He has a very good chapter 5 where he sort of derives all these numerical formulas for the quadrature. He even does Gaussian integration, which Kunin also does in a later chapter. And he does some other advanced methods, which I'll talk to in a second. So let me go back. So quadrature is stable. And right here I have some of the most famous quadrature formulas. There's the trapezoidal, which you basically take the endpoints, you use a factor of a half, and then all the other points, which are evenly spread out, you just add them up. Very easy formula to program and implement. Then you have the Simpson formula, which is a little bit more complicated. And here you have the endpoints. First you have the overall factor, which is h over 3, which is a little more complicated. Then the endpoints are 1 and 1, and then you have 4, 2, 4, and you just keep going until you end up with 4. But with Simpson's method, n has to be even. Then there's an even higher order, although it's not actually more accurate, which is the Simpson 3/8 formula. N has to be a multiple of 3 here. Very rarely you use this, but this is the formula. And here the repeating intervals, once you get rid of the endpoints, are 3, 3, 2. You keep on going 3, 3, 2, but you won't finish. You'll end up on 3. And the factor here is 3/8. And then there's a formula which Kunin calls Bodhi, but on Wikipedia I looked up and it's Boole. So I think there's some misspelling here. But anyway, this is an involved formula, 2 over 45, and the endpoints get factors of 7, and then it goes 32, 12, 32, 14, and repeating, but you'll end with 32. So the interesting thing about this formula, I think, is that this may be the last formula. I'm not 100% sure about this, but this may be the last formula of this type, which are called Newton-Cotes formulas, which has all positive coefficients. I think the next formula after this has some negative coefficients, and that leads to numerical instability. So let me go. Exercise 1.2 in Kunin is to compare these methods, and here's my Python program. Again, my programs are sparsely commented. I'll try and do better in the future, but also I'm not a software person, or so my programs are not the fastest or the best. Hopefully they're error free, but anyway, when you run this, you click in the box and you hit Shift Enter or Control Enter. If you integrate here, we're integrating a simple function, e to the x, but it's nonlinear, so any function, and I'm doing it from 0 to 1, and I just want to get an idea of the errors. So these are the errors. It's not the value of the function, it's the errors. And you can compare trapezoidal, Simpson, Bode, Simpson 3/8. Trapezoidal, it takes 128 points before you get an accuracy of about 10 to the minus 6. With Simpson, you get that kind of accuracy right away at about 8 points. Bode, you get that accuracy with 4 points. So it just shows you how strong these other formulas are. And eventually, like you can see with Bode, you hit the sort of the precision limit very quickly at about 128. Okay, so these formulas are, the basic foundation for numerically doing definite integrals. But you can do improper integrals, and you can do integrals with integrable singularities. But unlike, Maple or Mathematica, they do these things automatically. You don't have to tell it. It will know what to do. But Python doesn't. Maybe SciPy does. I don't know. We're not going to use SciPy much in this computational physics. But if you have an integral like the integral from 1 to b of dx gx over x squared, and gx is fairly constant when it's very big, this is going to converge very slowly. So it will converge, but if you try and evaluate it numerically, you basically have to take b infinity, which means you need a lot of points. So the best thing to do with these kind of cases is to make a variable change. If you do t equals 1 over x, changes the integral to the integral of b to the minus 1 to 1 of g of t inverse dt. And so that's an easy way to handle that. And sometimes you have formulas like this. You have integral singularities, like 1 minus x squared to the minus 1/2. It's singular at x equal 1, but it's actually convergent when you do the integral, because it's you can just verify that. When you change variables, here you want to make a variable change. You do this variable change, t equal 1 minus x, because you can actually factor this, and at x equals 0, you're fine. X equal 1, you have a problem, but you can factor out the two factors. One is no problem, and the other one is this factor. This is not the factor, but if you have 1 minus x to the minus 1/2, if you integrate that, it ends up being 1 minus x to the 1/2, which converges at x equal 1. It's just 0. So when you do this variable change, you get this expression, and this gives no problems. So always check your integrals. Make sure that if they have, we'll see how SciPy handles this a little bit easier, but you still have to tell it either by changing variables or doing something, that not to go ahead and just use our standard formulas, because once you get a 1 over 0, the program just halts. Runtime error. So Kunin has this exercise, which I solve in detail. The integral from 0 to 1 of t to the minus 2/3, 1 minus t to the minus 1/3 dt. This is actually a beta function, I believe. And you can evaluate this, and it's, 2 pi over the square root of 3. I know that's the answer. I'm not sure exactly how to evaluate this integral. I think I have to think about it. But Kunin wants you to use a quadrature formula and determine the accuracy. And he gives a hint. Split the range of integration into 2, and then make a change of variable in each integral. So the idea is it's easy to handle one change of variable. You can't do 2 at once. So we have integrable singularities at t equals 0 and t equals 1. So the first thing is just break this up. I chose 1/2. You don't have to choose 1/2. You could choose 1/3 and make this 1/3, but I think 1/2 works out easily. Now the first integral on over here, the one with the on the right hand side, the first one. This is integral at 0, or at least it converges if you do it right. And if you integrate t to the minus 2/3, you get about t to the 1/3, which does in fact evaluate to 0, so you won't have a problem. So that tells you, make the change of variable x equal t to the 1/3. In the second integral, we have an integrable singularity at t equals 1 minus t to the minus 1/3. And if we integrate that, we'll see that it's along the lines of 1 minus t to the 2/3. So I'm leaving out constant factors. You don't always have to use that factor for the change of variable, and I think it's a little easier to calculate if you just use x equal 1 minus t to the 1/3. Anyway, when you make these substitutions, which is routine calculus, you get two integrals. They actually now have the same integration limits, and you have these two functions. And so it ends up being the integral from 0 to 1 over the cube root of 2 of this function, 3 times 1 minus x squared, x cubed to the minus 1/3 plus 3x, 1 minus x cubed to the minus 2/3. And so at x equals 0, it's 1 to the minus 1/3, that's perfectly good, and 1 to the minus 2/3, that's perfectly good. And then at x equal 1 over the cube root of 2, when you, I wonder if I made a sign error here. Anyway, when you evaluate, when you take 2 to the minus 1/3 to the 3, it's 1/2. No, I'm okay. So it's 1 minus 1/2. So that both of these factors in parentheses become 1/2, and they're perfectly okay. So there's no more singularities, and you can use our formulas. And this code is basically a copy of the previous program. I just changed the function at the top. And then you can do it again, and let's look at the results. Again, these are errors. If you look at the trapezoidal, it takes a while to get to like 10 to the minus 6, takes 512 intervals, points. 2048, we're down to 10 to the minus 7th. Now, if you look at Simpson, we're down to 10 to the minus 7th at 64 intervals. Bode, we're at 32 intervals, we get 10 to the minus 7. And similarly for Simpson 3.8. So that's working well. It just depends on how accurate you want your results. But we'll find there are even more advanced methods, which I'm not going to cover here. They're covered in Chapter 5 of Newman's books. There are things like Romberg integration and adaptive techniques similar to Richardson extrapolation. It's kind of interesting how this all works, but you can get not only the value of the integral faster, but you get the error as well. So, if you're interested, you can look into it. But for the most part, Simpson or Bode is certainly good enough for the most part. But there are other methods where we will require more accuracy, and this is like the famous Gaussian quadrature method, which Kunin treats in Chapter 4 and Newman in Chapter 5. And it's a very interesting method, but the Gaussian quadrature does not have equal spacing. That's the key. It gets higher accuracy, but it gives up the equal spacing. Anyway, I just want to talk about SciPy. SciPy has a function quad, which is based on the original, I think, Fortran version in like 77. So it's been very well tested. And what you do, the actual function name is scipy.integrate.quad. Here I just imported as quad, so I can use quad. And I have just a bunch of examples, but like just to show you the code is very simple. For instance, to do that integral that we were doing earlier, it's just quad parentheses exp is the function, exponential function. This is actually the math exponential function. I could have imported the numpy exponential function. I think the numpy exponential function goes faster. Integrate from 0 to 1. You do that, you get the answer right away. Here's the answer. I'm not giving the error. We know the answer is e minus 1, and since e is 2.71828, 18284590, that's the limit that I know it. Here it goes like 3 decimal places more. You subtract 1, so you get 1 point. So this is the value, and it does it instantly and correctly. And it gives you an error estimate of 1.9 times 10 to the minus 14. So that's pretty good, not having to do any work or any programming. No special inputs. Now, if you go to the documentation, SciPy.integrate.quad, you see there's all these parameters, and they describe, okay, so it's the Fortran library quad pack, and they have all these parameters. It's very complicated. They explain them all, and some other functions you can look at, So they do have like Romberg for sample data, Simpson for sample data. There's adaptive Gaussian quadrature. I think this is being deprecated. A fixed order Gaussian quadrature. So there's a lot of functions that are in SciPy for integration. But this is just the basic quad, and it has a lot of parameters. Most of them you don't use most of the time, but some of them will turn out to be useful. So, and it has the usual examples. Going back to, like, here's an example where if you look at the second code box, it's easy to do improper integrals. Infinity just becomes np.inf. So here we are integrating, I do an example, the integral from minus infinity to infinity of e to the minus x squared. And all physicists know that this is just the square root of pi. So this is what the answer should be, the square root of pi. And if we do it by the SciPy, we use a quad. Now the function, I need to have the function defined. I could define it separately and then just put the name here. But I can do just a lambda function on the fly, e to the minus x squared. And then I do the limits, minus np infinity, minus infinity to plus infinity. And this is the exact, and this is the second line gives the exact same thing, about 17 places for this evaluation. That's because e to the minus x squared drops off so quickly that 6 standard deviations, you get everything. And then this is the error. The error is actually quite large here, but this is the maximum. The actual error is much less. So this is just an error bound, the second part of the tuple. Now singularities, again, they require some care, even if they're, I wrote removable here. So here I'm doing something where, like, let's say you're integrating sine x over x. As x goes to 0, sine x over x becomes 1. But Python doesn't know that. And so if you wanted to integrate this sinc function from minus 2 to 2, just do it using the quad thing, all of a sudden you're going to get an error. And basically it's telling you that it gives you not a number, NaN is not a number in Python. It just couldn't do the calculation. But it can do it if you just specify something to skip over that point. And 1 point in an integral doesn't mean anything. So this program here, it does it very quickly. Import quad, import np, define the function sinc, lambda of x, np sine x over x. And then what you do is you do quad, You do the function sinc, the limits -2 to 2, but you do points, and here I just have 1 point, 0 point. So actually it looks like a 0 comma there. Anyway, there's 1 point that we're skipping over. So once we skip over that 1 point, we're happy and we get our answer and we get our error bound. It's quite good. So that's all I have to say on Quadrature. And next week, in a few days, I will do the third of the methods in Chapter 1. These are the basic mathematical methods, which is finding roots. And I'm sure you've all seen that. There's basically like 3 easy methods. One is the bisection method. Another is the Newton-Raphson method. And then finally, there's the secant method. And so I will see you next week. Thank you for watching. Please leave any questions in the comment section on YouTube, or even better, go to my Piazza site, where you can, you can always leave questions here, and there's latex on the site. You use $2 signs for latex in Piazza, so you go $, put your latex, $. So I will update that notebook right now, and I will post this video on my Piazza site as well. And thank you for watching. I'll see you next time.